Welcome back, everyone, to geometry. We want to continue taking a look at section 20 regarding circles. All right, let's see. So the last thing we looked at was that 3 points determine a circle, something that we're familiar with. And so we want to move on to a couple of, or at least one new definition and a familiar definition, and then a couple of theorems. So a chord of a circle is a line segment whose endpoints lie on the circle. So if I were to consider a circle, then all that I'm referring to here is simply a line segment. Well, actually, why don't I go ahead and use a line, but a line segment whose endpoints are on the circle. So it's any such line that looks like this, okay? Line segment whose endpoints are on the circle. So it specifically has to be a line segment, of course. So that is a chord. Now it happens to be, of course, that we could actually have a chord that passes through the center of the circle. And if we have such a chord, then that chord is called a diameter. So a diameter of a circle is a chord that passes through the center is a chord that passes through the center Apparently I have a really hard time with these ends. The center of the circle. Excellent. All right. So we know what a chord is. We know what a diameter is. Let's go ahead and take a look at their relationships. So the diameter of a circle, of course, is the longest chord. That makes sense because anywhere else that I pass through the circle or have 2 points on the circle, they're going to be closer together because as I move a little bit one way or the other, I'm going to be shortening, right? If I were to move that way, it's shortening. If I'm moving that way, it's getting longer. If I move that way beyond the diameter, it's again going to get shorter. So it makes sense that the diameter is the longest. And it's this theorem that says exactly that. If AB is the diameter of a circle and CD is any chord in the circle that is not a diameter, then we have that the length of the line segment AB is longer than the length of the line segment CD. And really, in terms of proving this, the proof amounts to considering the triangle inequality. Excellent. So what do I mean by that? Well, let's take a look at a circle here a second. Let's actually make this circle black. That sounds a little better. And let's take a look at a couple of lines. Let's see. Let's make one of them a diameter. And let's make one of them not a diameter. Okay, 2 chords. One of them is a diameter, the other one is not. They don't have to be parallel to one another. That's not what we're saying at all. We're just having them not intersect for convenience to make things a little bit easier to visualize what's going on here. And if we were then to take take lines from those endpoints to the center of the circle, we have created ourselves a triangle. Okay. Now this side of the triangle is a radius. It goes from a point on the circle to the center. Same thing for this. So those lengths are the same as the length from the center of the circle to those points. So A, B, C, and D. So these lengths are the same, but we know that the sum of these two lengths is longer than that one by the triangle inequality. Hence, the sum of these two lengths, or simply the length from A to B, is longer than CD. So that's where we want to go with this. So step number 1, AB is a diameter of the circle with origin, let's say O, and radius OA. And then CD is a chord. Well, actually, let's say CD is not a diameter. That's what's given in the problem, right? AB is a diameter, CD is a chord that is not a diameter. Excellent. Well, O is not on the line segment from C to D. Why not? Well, that's simply the definition of a diameter. Right? CD is not a diameter, so O is not on CD, because a diameter is a chord that contains the center of the circle. All right, by the triangle inequality, we know that CO plus DO is larger than CD. CO plus DO is larger than CD. And that's the triangle inequality. All right. But we also know that AO is equal to CO is equal to DO is equal to BO. By the definition of a circle. And by the segment addition theorem, we have that AO plus BO is AB. Again, that's the segment addition theorem. So with this, we can make a substitution. We can plug AO and BO equals, sorry, actually we need to plug in, do this appropriately. CO plus DO is equal to AB. There we go. CO plus DO is equal to AB by a substitution of line 4 into line 5. Excellent. And now we can plug that into line 3. So we have that CO plus DO. Oh, sorry. That's already CO plus DO. AB is greater than, CO plus DO is AB, so AB is greater than CD. That's by a substitution of line 6 into line 3. And that's exactly what we wanted to show. So we're all set there. So again, the diameter of a circle is the longest chord. that is longer than any other chord. All right. Now there's, once we're, in other words, to theorem 20.6, I'm remembering that there's a correction on the names of this theorem and the previous. So the one we just looked at and 20.6. The word perpendicular, actually, you'll notice there's nothing perpendicular in this theorem. So if AB is a diameter and CD is a chord that's not the diameter, then AB is larger than CD. That has nothing to do with a perpendicular. However, if we notice here, given a circle, the diameter and a chord that is not a diameter, then those two things, the diameter and the chord, are perpendicular. Oh, hey, look. Perpendicular belongs in this theorem name. So the perpendicular diameter chord theorem says that if we have a circle, a diameter, and a chord that is not a diameter, then the diameter and the chord are perpendicular if and only if we have that the diameter bisects the chord. So bisects CD. And that proof is an exercise. So I leave that for you guys to consider. And that's all we want to take a look at in this video. So thank you again for your time and attention, and I'll see you guys again shortly for yet another video in section 20.